So in this final part of the first lecture, I'd like to talk a little bit about the Einstein-Den Haas experiment. Now, I need to stress that this is not examinable, but I think it's actually both interesting and quite helpful in elucidating some of the ideas in this course, and it's something that I will come back to a little bit later on as well when we've learned a bit more. Okay. So Einstein did this experiment with De Haas in 1915. And just to give you a little bit of context, so Einstein, primarily a theoretician, can't actually think of many other cases when he did some experiments. He knew Maxwell's equations extremely well. So 1905, 1907, he'd been working on the theory of special relativity, which really came about in thinking about how do Maxwell's equations, how are they compatible when we look at moving reference frames. Okay, and so he came up with the idea of special relativity. He'd worked a lot on aspects of solid state physics, atomic physics, the emerging ideas around quantum mechanics. At the time, 1915, he was working on general relativity. So how do you incorporate, how do you come up with a theory of gravity? And as he said, that was an exceptionally hard problem. And I think doing this experiment was a bit of, in a way, sort of easier relief for him, a diversion away from the tricky nature of general relativity. So at this point in history, people didn't really, we didn't have a proper formulation of quantum mechanics. We didn't understand how atoms work together in solids. So there was no clear consensus on the magnetic behavior of materials. It was not clear why iron was a magnet, for example. But Einstein knew Maxwell's equations very well, and you can see from Maxwell's equations that the only way you can create a magnetic field is to have some sort of current loop, a magnetic moment. And what Einstein thought was, well, there should be these sort of Amperian loops of current in a magnetic material. Okay, so there should be some sort of loop of current going around something like this and giving rise to a magnetic moment, okay, like this. So maybe this is an electron, the current is due to an electron, so it's an electron orbiting in some way. Now this was quite a controversial theory. There are some, without the full knowledge of quantum mechanics, it's not obvious how this is true. So it was quite controversial. But Einstein had a realization, which is that let's imagine that we've got a material. So we've got our little cylinder of iron, okay, and if all these little loops are all pointing in the same direction, that will give this material a magnetization M that points this way. Okay. If instead we had a cylinder that was magnetized in the opposite direction, what would that mean? Well, it would mean that all the current loops were going the other way round. Okay, so they were going this way round, and so the magnetic moments now would be pointing downwards. And Einstein's realization was that, well, this represents a change in angular momentum. Okay, so let's remember what angular momentum is. So angular momentum will be given by the moment of inertia times the rotational speed. Okay, and if that's, for example, just a point mass going round, that would be mr squared. I would be equal to mr squared, which is the the mass of the particle, and r is its distance around the point at the center of the orbit. Okay, and angular momentum is conserved. So, you know, if you sit on your desk chair and you spin yourself round, if you pull your arms in tight, okay, you are reducing r squared. So you're making your moment of inertia smaller, and in order to conserve angular momentum, you spin faster. If you put your arms out, you increase your angular momentum, and you can see that your rotational speed decreases. Okay, so these two states here and here represent different angular momentum. The angular momentum is the direction of the angular momentum is switched round. So there's a change in angular momentum. So this represents a change in angular momentum. In this case, if it's the electrons that are in some orbits, then it's the electron's angular momentum that is being changed. So what Einstein then realized was we could do an experiment in which we have a solenoid. Okay, we'll come to my slightly dodgy drawing of a solenoid. Okay, now you know that in a solenoid, the induced field is purely along the axis. Okay, so it's uniform in the center of the solenoid, and it's along the axis. So, and if I change the direction of the current, I'll change the direction of B. Okay. So what I could do is I could put in one of my little magnetic rods. Okay. So I'll do this in blue. Okay, there it is. There's my little magnetic cylinder. Okay. And I'll suspend it by a thin wire. Okay. And we'll arrange so that initially this has its magnetization pointing downwards. So we've got this scenario here. Okay. Now the B field from the solenoid doesn't exert any torque on M because they're both parallel to each other. It will try and push up or push down the rod, but that's fine. That'll be just taken up into account by the tension in the tension in the wire. So we wouldn't expect any forces acting here, any movement. Okay. But what we know will happen is if this is originally magnetized, so we've got a north pole and a south pole, the magnetization will change its direction. Okay, if you take a compass with a north pole and a south pole and you spend a long time stroking it with a magnet, you can switch it round. So the north pole becomes the south pole and the south pole becomes the north pole. What are we doing then? We're switching from this situation to this situation. Okay, so we can switch the direction of the magnetization in this iron rod. Okay. To do that, we must be changing the angular momentum, or so went Einstein's reasoning, in which case we were changing the angular momentum of the electrons. But angular momentum has to be conserved. So it's conserved, where does it go? Only place it can go is to the body itself. And so what we would expect to see in this experiment is a rotation. Okay, so the whole body should start rotating, and we switch the angular momentum from the electrons to the whole body itself. Okay. Now, how this experiment is often done is by reversing. You have quite a soft magnet, and you reverse the direction of the current periodically, and so you're just flipping forwards and backwards the direction of M. And you can see that this cylinder sort of twists one way, twists back the other way, and starts to oscillate due to the need to conserve angular momentum. So the important part of the Einstein-Den Haas experiment is to say, okay, we don't know what angular momentum is necessarily going on at a detailed quantum level, but what we do know is that angular momentum is closely related to magnetism. Okay, and when we change the direction of angular momentum, we change the when we change the direction of the magnetization, we change the amount of angular momentum. Okay, so there's a relation between these two things. There is a catch to this. Einstein saw this effect, but his interpretation of it, at least for iron, BCC iron, was not quite correct. If he had done his experiment a little bit more carefully and actually looked for real numbers, he would have discovered that there was a somewhat mysterious factor of 2 that should have been present if he'd done the experiment very carefully, and this was missed in 1915. Okay. So the effect he saw was correct. There's a link between angular momentum and magnetism, but it's not quite as simple as electrons going in little loops. Okay, and we'll return to this experiment in a few lectures' time when we've in a position to understand what was Einstein's mistake here. Okay, just a quick summary of what we covered today. We've looked at how magnetic fields can be created by moving charges from currents. We've looked at some definitions, some useful terms, the susceptibility, the B field, the H field. What should you do in preparation for next time? I would review back your notes on the quantum mechanics notes on the Schrodinger equation for the hydrogen atom. Both what you covered with Pete Nellist in prelims, but also what you covered at the beginning of Chris Patrick's course. Okay, and we'll use some of those ideas to start now to build up our quantum idea of the magnetic properties of materials.